A circular linked list is a sequence of nodes, where the last node points back to the first node, forming a closed loop. Each node typically contains two fields. First, data dash the value stored, and second, next dash a reference or pointer to the next node. Because the next of the tail links to the head, you can start at any node, and by following next repeatedly eventually visit every node and return to the starting point. Key properties. No null termination unless the list is empty where head equals null. The list can be traversed indefinitely. Useful for round-robin scenarios. The size of the list is still finite. A separate count variable is often kept for O of one size queries. Real-world analogy. Imagine a group of people standing in a circle holding hands. Each person knows who is on their right, and the last person's right hand is linked back to the first person, so you can walk around the circle forever. Linear singly linked list. Each node points to the next and the last node points to null. Linear doubly linked list. Each node has both next and prev pointers and the ends point to null. Circular singly linked list. Like a linear singly list, but the tail's next points to the head. Circular doubly linked list. Both ends are linked, so head.prev points to the tail and tail.next points to the head. Advantages of circular lists. Constant time insertion and deletion at both ends without needing a special tail pointer. The tail is reachable from any node. Natural fit for problems that require looping, for example round-robin. Memory usage is the same as linear lists, just one extra pointer per node or two for doubly circular. Disadvantages. Traversal must be careful to stop after one full cycle. Forgetting this leads to infinite loops. Certain operations, like searching for the end, are big O of n unless you keep an explicit tail reference. Debugging can be harder because a null pointer is no longer a clear sign of list termination. Insertion. 1. Create new node n with data. 2. If list is empty, head equals null, set n dot next equals n, head equals n, and tail equals n if you keep a tail. 3. To insert after a given node x. N dot next equals x dot next. X dot next equals n. If x was the tail, update tail equals n. Deletion. 1. If list is empty, nothing to do. 2. To delete node x given reference to previous node p. P dot next equals x dot next. If x is head, set head equals x dot next. If x is tail, set tail equals p. Free x or let garbage collector reclaim. Traversal. Start equals head. Do. Process start dot data. Start equals start dot next. While start not equal to head. Pseudocode language agnostic. Insert after head tail ref node value. New node equals node values. If head equals null. New node dot next equals new node. Head equals new node. Tail equals new node. Else. New node dot next equals ref node dot next. Ref node dot next equals new node. If ref node equals tail. Tail equals new node. Delete node head tail previous node. If head equals null, return. Del node equals previous node dot next. If del node equals head. Head equals head dot next. If del node equals tail. Tail equals previous node. Previous node dot next equals del node dot next. Free del node or let GC handle it. For any circular linked list with n nodes. Insertion at a known position given previous node takes O one time, because it requires only a constant number of pointer updates. Deletion given the previous node also takes O1 for the same reason. Insertion or deletion at the head when you keep a tail pointer is still O1, update head and tail accordingly. Searching for a node by value or locating the previous node, when only the target node is known, requires a full walk around the list, which is ON. Space complexity. Each node stores data plus one pointer singly circular, O1 extra space per element. If you maintain a tail reference and a size counter, the overall extra space is O1 regardless of n. Thus the list is memory efficient and provides constant time updates at known locations, while arbitrary searches remain linear. Explanation: let t sub insert of k be the time to insert a new node, when we already have a reference to the predecessor node in a list of size k. Allocate a node constant time c1. Set new node dot next equals pred dot next c2. Set pred dot next equals new node c3. Possibly update tail pointer c4 executed at most once. Hence t insert of k equals c1 plus c2 plus c3 plus c4 equals O of 1, independent of k. Similarly for deletion, given predecessor pred. T delete of k equals c5 store del equals pred dot next plus c6 pred dot next equals del dot next plus c7. Adjust head slash tail plus c8 free equals O of 1. If we denote the number of steps as a recurrence t of n equals t of 1 for any n greater than or equal to 1, which solves to a constant. This mathematical proof shows that insertion and deletion are theta of 1 when the needed neighbor node is already known, confirming the practical observation. If the predecessor must be found, the recurrence becomes t of n equals t of n minus 1 plus O of 1, solving to O of n, which matches the linear search cost. Linear to circular. Given a linear list with head h and tail t, set t next to h, the list becomes circular. If the list is empty, keep head null. To break a circular list back to linear, locate the tail node whose next equals head and set tail next to null. Singly to doubly circular and vice versa. Converting singly circular to doubly circular, traverse the list once. For each node, set node prev to the previous node, keeping a variable prev. After the loop, set head prev to tail and tail next to head. Converting doubly circular to singly circular, simply ignore the prev pointers, optionally set each node prev to null and keep only next links. The circular property stays because tail next already points to head. All conversions require one full pass over the list, O of n time, and use only a few extra pointers, so O of 1 extra space. Write pseudocode to insert a node after a given position k in a circular singly linked list. Explain why the algorithm is big O of 1. Given a circular doubly linked list, delete the node that contains value x. Show edge case handling when x is at head or tail. Prove that rotating a circular list by m positions can be done in big O of m time and big O of 1 space. Convert a linear singly linked list to a circular one and then back. Illustrate the pointer changes. Always keep a reference to the predecessor when deleting. If only the target node is known, use the copy next node trick. Copy data from next node and delete next. Works only for singly lists. For round-robin scheduling, maintain a current pointer that moves to current dot next after each quantum. For Josephus, repeatedly delete every kth node by moving a pointer k-1 steps, and then performing big O of 1 deletion. Answer structure: describe initial state, algorithm steps, update of head slash tail, and complexity analysis. Josephus problem: n people stand in a circle. Every kth person is eliminated until one remains. A circular linked list models the circle perfectly. You move k-1 steps using next pointers, then delete the kth node in O of 1. The process repeats n-1 times, giving O of n times k overall, or O of n if k is constant. Round-robin scheduling: each task is a node in a circular list. The scheduler holds a pointer to the current task. After giving it a CPU slice, it moves the pointer to current dot next. Insertion of a new task, for example when a process starts, is O of 1 by inserting after the current tail. Music playlists shuffle loop. A circular list lets the player loop back to the first song automatically. Cache replacement policies like the clock algorithm use a circular list of frames with a hand that sweeps around, marking pages. The circular structure enables the hand to wrap around without extra checks. Type definition of struct node with integer data and a pointer to struct node named next. Type name node. Node head equals null. Function insert after returns pointer to node, takes pointer to node called prev and integer value. Allocate new node as malloc size of node. Set new node dot data equal to value. If head equals null, then this is the first node. Set new node dot next equal to new node. Set head equal to new node. Return new node. Otherwise, set new node dot next equal to prev dot next. Set prev dot next equal to new node. Return new node. C++ using smart pointers can replace raw malloc free with standard unique pointer. Class node with integer data and a reference to node called next. Constructor takes integer d and assigns data to d node head equals null. Function insert after takes node prev and integer val, creates new node n as new node with val. If head equals null, then set n dot next equal to n, set head equal to n, return n, otherwise set n dot next equal to prev dot next, set prev dot next equal to n, return n. Empty list head equals null. Single node list where node dot next points to itself. Insertion or deletion must update head correctly. Deleting the head when it is also the tail, which is a single node, makes the list become empty. Keeping a tail reference simplifies constant time insertion at the end and makes size queries trivial. In languages with garbage collection, such as Java, explicit free is unnecessary, but you must remove all references to a node to allow reclamation. Beware of infinite loops during traversal. Always stop when you return to the starting node. Overall, the logic is identical across languages. Only the syntax for memory management and pointer handling changes.